Standard statistical mechanics assumes random systems follow pure chaotic probability, where the observer's sampling parameters dictate the expected output. The golden set, a discrete bounding array built from Fibonacci or Tribonacci nodes, overturns this assumption. We can observe this by running a 100-step Monte Carlo accumulator, an analog thermodynamic solver, using a 5-node Fibonacci set, 13, 21, 34, 55, and 89. While the initial steps observe random, the cumulative mean of the system becomes locked at exactly 42.4. This is topological ergodicity. Inside a bounded golden set, the stochastic chain becomes deterministic. Even if an observer skews the local probabilities to favor certain nodes, the geometric mass of the integers acts as a physical funnel that overpowers that noise. This creates mathematical friction, where continuous statistical models drag against unyielding discrete integer constraints. Measuring this exact topological friction allows us to decompile the structural boundaries of the observable universe. This friction natively exhausts fundamental physical constants, specifically Pauli's fine structure constant, 137. At the macroscopic level, physical reality fills a predefined, rigid topological mold. Evaluating stochastic runs with standard linear means is imprecise because the probabilities drag the results away from their geometric centers. This is topological phase drag, a downward pressure exerted by the golden lattice on continuous statistical models. We correct for this using the L2 norm lift. Instead of linear averages, the Monte Carlo mill evaluates the squares of the variables. As the space squares, the golden lattice expands. This increased weight crushes the probabilistic noise into the bottom axis. Squaring the space creates a high-pass filter, stripping away phase drag. The resulting ratio locks on to 1.6197, matching the golden ratio. A microscopic log residual gap of approximately 0.001 remains between the empirical ratio and the transcendental limit. We define this gap as the thermodynamic exhaust of the simulation. It represents the physical heat generated by crushing 100 randomized integer squares into a one-dimensional continuous boundary. The L2 Euclidean space proves that continuous statistical mechanics are slaved to the discrete topological mass of their inputs. We now shift the Monte Carlo mill into three-dimensional space by drawing from the Tribonacci sequence. This transition triggers a catastrophic increase in statistical variance. In 3D space, the metric mass scales by alpha squared, or 3.383, making the upper nodes much more dominant than in Fibonacci space. This creates a heavy-tailed Pareto distribution. A single node now accounts for over 70% of the set's entire geometric volume. Slight undersampling of this massive node causes the macroscopic expectation of the system to collapse. To stabilize this 3D volatility, we replace the integer array bounds in the generator with a continuous irrational scalar, 2 phi. This 2 phi probability sieve restricts the sampling range, forcing the Monte Carlo mill to draw discrete integers using irrational probabilities. This architecture forces the Tribonacci summation law into a flawless fusion with the golden ratio. The continuous boundary acts as a geometric prism, trapping the probabilities inside an algebraic collapse that reduces the expectation to the Tribonacci node divided by phi squared. Injecting continuous boundaries into the generator stabilizes the 3D volume, proving that discrete integers and irrational probabilities can exist in a zero-friction state. We can now apply continuous calculus to this discrete matrix using a 4-3-2-1 differential drop on the Tribonacci polynomial. We sweep the derivative operator across the sequence and apply Vieta's formulas to extract the product of the roots. The derivative reduces the fourth-degree polynomial to a cubic state. At the sequence's ninth rung, the roots product resolves to the fraction 137 over 88. 137 is the exact numerator exhausted by this calculation. Its pre-reduced mass in the polynomial is 274. 274 is the 12th Tribonacci node, representing the geometric mass of the 12th spatial dimension. Dividing this 12th dimensional mass by the spin 1/2 quantum dyad yields 137. This mirrors the Standard Model's 12 fundamental fermions, where electromagnetism emerges as the differential exhaust of these particles. This structural coupling explains why the physicist Wolfgang Pauli found the fine structure constant, the value 137, locked into the foundations of electromagnetism. The continuous discriminant of this system factors into 5 times 137 squared plus 4. This incorporates 137 into the absolute signature of golden topology, coupling the 3D Tribonacci sequence to the 2D golden plane. Fundamental physical constants manifest as the differential exhaust of discrete integer geometries. This differential friction exists in the gaps between integer derivatives. We can map these fractional spaces by moving into phase space using the fractional Fourier transform. Here, a fractional derivative is evaluated by multiplying the frequency by the imaginary unit raised to a fractional power. In physical space, a lens acts as the transform boundary. As a sharp square wave passes through, it physically melts into a continuous oscillating wave. This is the spinorial twist. Executing a fractional derivative physically rotates the topological phase of the universe in the complex plane. The spaces between dimensions consist of continuous optical rotations, blending discrete geometry into physical waves. While fractional space melts into waves, polynomials pushed to extreme high-dimensional limits behave with rigid precision. At these scales, the golden set is governed by the law of topological compression. By elevating the dimensions through the dyadic octave lift, the system violently sheds the curvature seen in lower dimensions. As the 64th degree manifold is reached, the geometry crystallizes into a rigid Euclidean square, the unit box. We can identify 8 fractional scars where the continuous boundary bulges, unable to fully overcome the friction of the discrete Fibonacci integers. At the extreme limits of dimensional frequency, the universe manifests as a rigid Euclidean box, the result of unyielding mathematical friction between discrete integers and continuous space.